Okay, we're going to keep on moving with acid-base problems. In this situation, I want to point out and identify my acid and my base. I see that this is an ionic compound in which it actually exists in this form, right? So that way we know that this is the base, and this way we know that this H has to be the acid. And bear with me here and I'll explain why this is the acid and not this alkane H. So as long as you trust me at this point, we're going to draw our base, grab this H, and then because carbon is more electronegative than hydrogen, the H, or the bond to the H, snaps onto the carbon. And we end up with a gross situation called a carbanion. Now the question is, well, what way is the equilibrium going to lie? And so we have to interpret between these two bases what is more stable. So let's make a little discussion chart. I have to decide between these two bases what is more stable, and that is going to dictate the direction of the equilibrium. Well, let's think about our 5 factors. Everyone always wants to talk about electronegativity because granted, or giving it its proper support, yes, it is a very profound and important effect. So let's talk about electronegativity. Well, we know that the nitrogen's electronegativity is larger or better or more affinity than carbon's electronegativity. So that is a factor that is pushing us in the left-hand direction for stability stakes. We don't really talk about size because remember, that's if we're talking about elements in the same column. Nitrogen and carbon are in the same row, so we talk about electronegativity. So nitrogen is more electronegative. There's no resonance. If we did the rule of 3, 1, 2, 3, there's no double bond between 2 and 3. We can't resonate this. Nothing exists for resonance. Inductive effects, again, we're not going to talk about them right now because we have electronegativity at play, which immediately is going to outweigh induction. And we also see we have hybridization. The reason why we want to talk about hybridization is because this is a situation that is very important. And let's just write this here. What we have benefiting the right side is an sp hybridization. And let's talk about this. Here's my nucleus. Here is what I'm telling you would look like if I had an sp3 hybridized orbital. If I have an sp hybridized orbital, do you see how it's much smaller? And the distance from the nucleus to the charge is much smaller. And let's think, what exists at the nucleus? Well, we never talk about them, but protons. And what stabilizes what? Well, we know opposite charges attract and net each other out to neutrality. -1 plus +1 is 0. That is a stabilizing factor. If you can get your charge closer to this nucleus, or through hybridization, you have more S character. And that is the fancy way to explain that you have more nuclear stability because this negative charge is in closer proximity to the protons that are housed in the nucleus. Because of that, hybridization plays a stabilizing factor in this molecule. And the question now is the electronegativity of nitrogen outweighing the electronegativity of carbon more important than the hybridization stabilization factor? And you gotta just trust me on this one, and this is why I wanted to show you the equilibrium lies to the right. And that's not cool because we're kind of prepped and predispositioned to believe that electronegativity is the end-all be-all, right? Nitrogen, more electronegative, carbon, carbanion, gross. But the sp characteristic of hybridization, bringing that charge down to the nucleus, is actually more substantial than nitrogen's electronegative characteristic. And that's because nitrogen, while it is more electronegative than carbon, it's not that much more to the point where it outweighs the hybridization. And to kind of go off of that, let's talk about pKa values. Well, we know in amine, we should have memorized all these, is 35, and an alkyne is 25, which means that this hydrogen has a pKa of 25. If we draw an alkyne, alkane, this pKa is 55. If we draw an Alkene, this H is 45 pKa. Do you see how incredibly different the pKa value is for an alkyne versus an alkane, or even an alkene? The hybridization of being sp versus sp3 or sp2 is not just an insignificant increase, it's 30 orders of magnitude different. Which goes to show you that having something sp hybridized is not a subtle effect. The hybridization increases the acidity in a huge way. And so when people ask the first couple of weeks, well, can we draw in the H on the terminal alkyne? It's like, yes, I absolutely would prefer you to draw on that H, because what we find out is because of hybridization, this H is so important because it's weakly acidic now that there's a lot of chemistry that can happen with it. And because of that, we can just draw it in and it becomes an important H. It's not like every alkane's H where they're very, very not acidic. So the big takeaway from this top problem is the equilibrium goes to the right because of hybridization. So let's think about this bottom structure now. Well, very similar to the top, we have an ionic situation in which we can redraw this as a carbanion and then an alcohol. Well, I know that this is our base now because we have a negative charge, so this is going to go. And because oxygen is more electronegative than hydrogen, the bond will snap on to favor that electronegativity. And we end up with a very similar but different situation. And so now we have to decide again, much like before, sorry, let me redraw that. What is more favored? The alkyne due to sp hybridization, or the O electronegativity outweighing carbon's electronegativity? And so the same two factors are at play, electronegativity and hybridization. But now we have oxygen as the electronegative atom as opposed to nitrogen. And what we find out is that the equilibrium lies actually to the oxygen, and the electronegativity wins. Before, hybridization was more profound of an effect or more substantial of an effect than nitrogen's electronegativity, but oxygen is way more electronegative. And because of that, it actually carries the winning justification over hybridization. So because of the differences between having a nitrogen charge and an oxygen charge, electronegativity favors the bottom reaction scheme, but hybridization favors the top. And if we think again about pKa values, alkynes are 25 and alcohols are 15. It favors the side of the higher pKa. Similar question, but different. And that's one of those things why you can't just do these problems once and then think you have a hang of acid-base chemistry, because you'll have something so similar yet have a completely different result on what equilibrium is being favored. And that's just, you have to do these problems and see all different types of angles and see outline situations and make your best logical choice. Again, knowing pKa values is extremely beneficial because it can provide a fantastic verification to a complex problem.